Last time we had talked about collinearity rules. So for instance, if we ever need to take the derivative of a constant times a function, it turns out that we can simply take the constant outside of the derivative. So in Leibniz notation, that statement would look like this, or in prime notation, we could write it like that. Now similarly, if we ever need to take the derivative of a sum or difference, it turns out that the derivative can be distributed. So in Leibniz notation, it would look like this, or in prime notation, it would be simply f prime plus or minus g prime. Does this type of rule extend to other situations? So we'll talk about something called the product rule. And really the best way to start is it true that if I were to take the derivative of a product of functions, is that equal to the product of their derivatives? And the answer here is a big no. If I were to say, take the derivative of x squared. Now, I already know that this is equal to 2x, but at the same time, there's nothing preventing me from writing this as x times x. Now, if I were to make use of this nonsense rule, this is the derivative of x times the derivative of x, which would be 1 times 1. And certainly 2x does not equal 1. So there is an example that shows me this rule is not correct. So what is the correct product rule? As always in math, we need to start with a definition. We have to assume that the functions we are using are going to be differentiable at the points we want them. So that means that these f prime and g prime expressions exist. So the proper place to go is to talk about this derivative using the limit definition. So this entire thing inside of the derivative is regarded as our function. So it would be the thing in the purple box evaluated at x plus h, subtract the thing in the purple box evaluated at x, all over h. To sneak a peek, as always, you'll get a 0 over 0, which is true for any derivative expression, which means you can't use any limit laws. What you should be doing is using some algebra. Now, in the situation when the functions are unknown, when they are general like this, the algebra you can do is somewhat limited. We are going to add 0. Now, the 0 I'm going to add, it's not just going to be this symbol. It's going to be something that gives me more pieces to play with, but is mathematically equal to 0. And after a lot of trial and error, it turns out that this is one of the forms of 0 that will work. F of x times g of x plus h, subtract the same quantity. And so we go to our definition, the mess that we have. What we want it to do is to look different, but be mathematically equivalent. So I'm going to take this thing and plug it in, the negative first, and then I will put the other part of it in. So that is all that I've done is put in effectively a 0. I have not changed the value of the expression. All I have done is change the way it looks. So in these first two terms right here, there's a common factor. There's a common factor of g of x plus h, sorry. So when I factor that out, I'll be left with f of x plus h minus f of x times the g of x plus h. And in the second two, the common factor this time is f of x multiplied with g of x plus h subtract g of x. So all I've done is taken out the common factor in each bunch. And if you look at the first two terms, I see an f of x plus h minus f of x. That's starting to look an awful lot like the definition of the derivative of f. Now, each one of the expressions is over a common denominator of h, which means I could write them individually as a fraction with the denominator of 8, and at the same time, I can do the same expression over here for the second term. Is it ready for the limit laws? Now, you can only use the limit laws if all these constituent limits exist. As far as the limit with respect to h is concerned, this thing is a constant because it has no h's, so its limit exists. We assumed that f was differentiable. So that means this exists. We also assumed that g was differentiable, which means that this limit exists. We need to know if this limit exists. Well, since g is differentiable, that means g must be continuous by the theorem. And because g is continuous by the theorem, I can pull the limit inside. And that means I would get g with the limit as h goes to 0 of x plus h. This thing would just be g of x. And that limit would exist. So it turns out that yes, all of these limits exist. And when I apply the limit laws, I will get something that looks kind of messy, but is actually mathematically really nice. Because now I get a nice, wonderful expression in terms of limits that I know exist. And at the end of the day, I end up with f prime of x times g of x plus f of x times g prime of x. So in fact, this is the correct product rule. Not because I want it to be, but because the definition of the derivative tells me that's how it needs to be. If I want to take the derivative of a product, I have to differentiate one function, leave the other one constant, and keep the product there, and then reverse the story. So f prime g plus f g prime. And this rule makes a lot of sense. Remember that the order of a product doesn't matter. So if I decided to put the g in front of the f here, this rule turns out to be exactly the same. The order of multiplication doesn't matter, so the order of differentiation doesn't matter either. The rule is smart enough for us to figure that out. Now, we could go back to the example that I did at the beginning and say, okay, this thing here, x squared, could be written as x times x. And if I wanted to, I could consider one of the x's as an f, the other one as a g. According to the product rule, this would be the derivative of the first one times the second. So that would be f prime g plus the first times the derivative of the second. So that would be f g prime. And now I'm hoping that you can see the rule will produce the correct result. We will end up getting x plus x, which is in fact 2x, like it's supposed to be. And so once you know this product rule, if I had an expression like this, let's make it an x cubed just for fun. So if I had an x cubed, this could be regarded as f, and this could be regarded as g. So the product rule says take the derivative of the first one, multiply it by the second, then add it to the first one times the derivative of the second. So it becomes a very mechanical process. The derivative of x cubed is 3x squared. Now I'm going to be really detailed here and say, okay, the derivative of a sum is the sum of two derivatives. Now, we won't do that going forward because we'll just become so comfortable using the rules, but it's just nice to see how they work here. So I'll get 3x squared, 1 plus e to the x, plus x cubed, 0 plus e to the x. And so this will end up giving me 3x squared, 1 plus e to the x, plus x cubed, e to the x. Now, you could be lazy and leave it like this, but more often than not, it's going to be to your advantage to try to factor these expressions as much as possible. A lot of what we do in Chapter 4 will rely on us factoring expressions as fully as possible. So for instance, we could write it as 3x squared plus these two terms. These two terms can be factored into a 3 plus an x. And then the final thing that we could do is take out an x squared out of all of these terms and write it as 3 plus e to the x times 3 plus x.